In the first module, we have seen how to determine the endurance limit of materials, basically steel and other materials like aluminium. Statistical data is available which relates the endurance limit of a material to the ultimate tensile strength of the material. It can be seen that SE dash is equal to 0.5 times SUT when SUT is less than or equal to 1400 MPa, and SC dash is given as 700 MPa when SUT is greater than 1400 MPa, where SE dash, as we have seen in the previous module, is the fatigue strength, or I would say endurance limit of rotating beam specimen, and SUT is nothing but the ultimate tensile strength of the material. Or UTS of material. It is important to note here that SE dash corresponds to the fatigue strength of a rotating beam specimen, or in other words, it is nothing but a laboratory specimen. When we come to an application, the endurance limit of a material is different from the endurance limit of a rotating beam specimen. The endurance limit will be the SE dash multiplied by some modifying factors, which we will be seeing in the next module. And in the first module, we have seen that ferrous alloys like steel have well defined endurance limit. Alloys have well defined endurance limit given by the knee of the SN diagram, and we have seen that other alloys, non-ferrous alloys and aluminium alloys, do not exhibit endurance limit. This we have seen in the previous module. And for these materials, we have the term called fatigue strength of the material. Fatigue strength of the material, which is defined as the stress corresponding to a given number of cycles to failure. That is, if I am told that a material has to withstand 10 power 5 cycles, then what is the stress corresponding to that number of cycles? That is called the fatigue strength of the material. And this can be determined from the SN diagram. And important fact is that SN diagram is plotted on a log scale. That is, for example, I can show you that if I have a graph like this, where I have the x-axis and y-axis, and if I have a straight line, the equation of the line is given by y is equal to mx plus c. This everybody should be clear with this. Similarly, in SN diagram, we can say we have log y plotted against log ax, where log x is nothing but the log of number of cycles and y is nothing but the fatigue strength of the material. And if I have a line, suppose like this, now what will be the equation of this line? It will be log y is equal to log x plus into M plus C. So this should be clear. Once this is known, then we can easily find out what is the fatigue strength of the material given the SN diagram. We'll try to solve a problem which makes it very clear. Now we will try to find out the endurance strength of a specimen for a given life. Okay. Now we have a problem here. A rotating beam specimen made of steel of grade 45C8 which has an ultimate tensile strength of a rotating beam specimen made of steel 45C8 with ultimate tensile strength of 630 megapascal is subjected to a completely reversed bending stress. What is the calculate the endurance strength of the specimen for the life of 90,000 cycle? Now how to go ahead with this problem? We have already seen this curve, the SN diagram for the steel. We have seen that it has got three straight lines. Initial low cycle fatigue region, then we have 10 raised to 3 to 10 raised to 6 cycles, then we have the high infinite life cycle. Now 90,000 cycle means it comes somewhere in between this thing, in between 10 raised to 3 cycles and 10 raised to 6 cycles. So if it has to withstand 90,000 cycle, what is the strength corresponding to that 90,000 cycles? So how to find this? We will try to make the SN diagram for our case. Since it lies between 10 raised to 3 and 10 raised to 6 cycles, we will try to enlarge this portion of the diagram as shown here. Now we will draw the SN curve for this problem. It looks something like this. We say that this second straight line we have considered here. The starting point is at log 0.9 times SUT. This point corresponds to log of SC dash, where SC dash is the endurance limit of a rotating beam specimen. And in the x-axis, this point corresponds to 10 raised to 3 cycles. So log of 10 raised to 3 cycles is nothing but 3. And this point, the endurance limit, corresponds to 10 raised to 6 cycles. The log of 10 raised to 6 is nothing but 6. And the important thing is, here the logarithm is taken as a natural logarithm. So now what will be the log of 0.9 SUT? So log of 0.9 SUT, where SUT is nothing but SUT is given as 630 megapascal. Therefore 0.9 SUT is nothing but 567 megapascal, and log of 0.9 SUT to the base 10 is nothing but 2.7536, and this is nothing but written here. And log of SC dash is given as, we have seen in the earlier module, in the first portion of this module, we have seen that SC dash is given as 0.5 times SUT when SUT is less than or equal to 1400 megapascal, and if it is greater than 1400 megapascal, it is taken as 700 MPa. Therefore here SUT is given as 630 megapascal, which is less than 1400 megapascal. So we can take SC dash as 0.5 times SUT, that is nothing but 0.5 times 630 megapascal, which is nothing but 315 megapascal. And log of SC dash will be 2.4983. This is written here, 2.4983. Now the problem gets simplified. So we have first point here 2.7536, second point here 2.4983, and the corresponding x locations are 3 and 6. Now we have the number of cycle given as 90,000 cycle. We have to find the stress corresponding to it. What I can do is, I can draw a line here and say this corresponds to 90,000 cycle, or I can put as log of 90,000 cycle. Okay, I can the problem details can be written as this. So we have 10 raised to 3 cycles here, 10 raised to 6 cycles here, the log is 3 and 6 correspondingly, and we have 90,000 cycle coming in between these two. So and the value corresponding to log of 90,000 is 4.9542. Now the problem is that we had to find the endurance strength corresponding to this number of cycles. So we have to find what is the y coordinate of this point. That is the only thing we have to find out. So we have seen in geometry that if you have a line, the first point is given by x1 y1, second point given by x2 y2, and if you want to find the coordinate of point x y here, from the equation of line we can write y2 minus y1 by x2 minus x1 is equal to y minus y1 by x minus x1, or we can write as y minus y1 by y2 minus y1 is equal to x minus x1 by x2 minus x1. This is from the geometry, we can find out like this. And here what is x1 and x2? In our case we can say x1 is equal to 3, x2 is equal to 6, x equals 4.9542. This x1 is the x coordinate of this point, that is nothing but 3, and x2 is the x coordinate of this point, which is nothing but 6 here, and x is the x coordinate of the point which we want to find out, that is 4.9542. Similarly, y1 is nothing but log of 0.9 SUT, that is the y coordinate of this point, that is 2.7536. y2 is nothing but the y coordinate of this point, that is nothing but 2.4983, and y is what you have to find out. So what you can write? We can write it out as, from this equation we can write y minus y1 by y2 minus y1 equals x minus x1 by x2 minus x1. So what is y here? Y is what we want to find out. So y minus y1 is 2.7536 divided by y2 minus y1. y2 is 2.4983 minus 2.7536 equals x minus x1. X is what? X is 4.9542 minus x1 is 3 divided by x2 minus x1. x2 is 6, 3. So this is becomes y minus 2.7536 divided by 2.4983 minus 2.7536, nothing but minus 0.2553. This is equal to 4.95142 minus 3 is 1.9542 divided by 6 minus 3 is 3. So we can write as, this becomes y equals 2.7536 plus minus 0.2553 into 1.9542 divided by 3. Minus 0.1663, that is nothing but plus 2.7536. This is nothing but 2.5872. So how do we check whether this is okay or not? We can check by seeing that whether it comes between the two limits. 2.5872 definitely comes between 2.4983 and 2.7536. So we can say this will be the right answer. So what will be the fatigue strength? It will be, so therefore the fatigue strength will be the anti-log of this. Anti-log of 2.8572, that is nothing but 2.5872, 386.5. So therefore we can say that the fatigue strength corresponding to 90,000 cycle is nothing but 386.5 megapascal. So this way you can find out what is the fatigue strength of the material corresponding to any given number of cycle. So only thing we have to keep in mind is, here also it is only a straight line equation, but instead of x, y, x1, y1, x2, y2, we have log values. So in this one, you should keep in mind that we have to take the log values in both the x-axis and y-axis, and finally to find the answer we have to take the antilog of the answer. So that will give the fatigue strength corresponding to a given number of cycles to failure. So with this we can find out how to find out the fatigue strength of the material. Now we can slightly modify the question. So this kind of a design is called a finite life design, because we are designing the component for a finite life of 90,000 cycle. Now if I ask to design the component for infinite life cycle, so how can we design? In that case, what should be the design criteria? That is, this is for a finite life design. That is what we have seen. If we want the component to say for infinite life cycle, what we can say? We can say that the stress coming in the component should be less than or equal to the endurance limit of the material, or we can say that it should be less than or equal to 0.5 SUT, that is nothing but 315 megapascal. So if the stress is less than 315 megapascal, then it will undergo infinite number of cycle. Therefore this is the criteria for designing the component for infinite life cycle. And for a finite life cycle, then this is the method which we have to find out the strength for the finite life design. So same problem, we can design the component for finite life as well as infinite life. Finite life means we have to find out what is the strength corresponding to the given number of cycle. If it is an infinite life cycle, the problem is to find out what is the endurance limit of the material. With this we come to the end of this module. In the next module we will see what are the endurance limit modifying factors.